So now we will start with exercise sheet 3.2. The first one is about vector space, a vector space or vector spaces in general, in this case over R3. So it means three-dimensional space. And we have different bases and the questions are about, for example, converting given vectors from one base, from one basis to another, and so on. And I have to comment about this notation with squared brackets. So in general, it's like if I write squared brackets, vector A, comma, vector B, for example, what this means, this is just a short notation for the set of all possible linear combinations of these vectors. It might be 2 vectors, 3 vectors, as you see here, and so on. So in this case, it's, you could say, it's the set of all vectors, let's say x. So that, and of course, element, in this case, it would be R2, if it's a 2-dimensional, or not really. It might also be R3. We are still inside R3. Okay, let's put it this way. So that this vector x equals, let's call it x1 times vector A plus x2 times vector B. And now what you see here, this is called a linear combination with some real number x1 and x2, like weighting factors, to build a new vector using the basis of, or using, if this is a basis, using this set of vectors. And so the question is, which is the subvector space of R3 that is spanned by these 2 vectors? And the answer is then every vector that can be put in this form. And so you know what it is? It's a plane which is spanned by these vectors A and B. So it actually is something special, but Martin defined what a linear combination is. And this is a very central technical term actually in this context to understand what is a linear combination, because it's also the basis for terms like linear dependence and linear independence. Is that fine so far? Understood? I hope so. Okay, thanks. And so we can start. And actually, yes, it's like I supposed. In the first part, we should make sure that these 3 vectors given with coordinates 1, 2, 1, 2, 1, 0, and 0, 1, 2, called A1, A2, A3, form a basis of R3. What do we have to consider for a set of vectors to be a basis of a vector space? The answer is, firstly, and that's point 1 here, or item 1, firstly, the number of vectors that I use here must be exactly equal to the dimension of the vector space. So this is the only chance that I have to span the whole vector space if I use the right number of vectors. So if I use less than 3, I could never span a whole 3-dimensional space. But also more than 3 vectors for a basis would be definitely too much, because the 4th one would definitely be linearly dependent from the others, or they would be linearly dependent from each other necessarily. That's just a fact which can be proven and which has been proven, I think, even by yourselves inside the lecture. So anyway, we need 3 vectors. I wrote it this way: 3 vectors, 1, 2, 3 is fine, since n equals 3. N is the dimension or dimensionality of the vector space. That's fine. The second item is more difficult. Now we must show that the set of vectors A, I just wrote short notation A vector I. This is just a placeholder for 1, 2, 3. You know. So our base. This is the base A. The basis A. If it's valid, they must all be linearly independent. And you also know that linear independence, if it turns out to be true, so if the vectors are linearly independent, it means they are linearly independent from each other. On the other hand, if they are linearly, this is about linear independence. So I start out with linear independence. Okay, if they are linearly independent, they are independent from each other. If they are linearly dependent, it means that any one of them is linearly dependent on the set of all others. Okay, so that is just, it's a property which is not which is never exclusively given for one of these vectors, but all at once for all of them. That's perhaps important to understand. Okay, so now let's start. What is the official definition of linear independence? That's now our point. And here you see it again, what I just wrote in blue color. This is a so-called linear combination constructed by use of all these vectors, A1, A2, 3, by giving them a scaling factor, real number, and then adding them by the rules of vector addition, of course. But now, this is done in a special way. The linear combination, which I built here, is by, you could say by definition, is chosen to be equal to the zero vector. Then you know what it is. This is the neutral element of vector addition. So the idea is to construct a so-called closed vector chain. This is a term I will use also in the last optional exercise again. A closed vector chain is just, it's like you go around. Yes, you make a round trip. That's it. Okay, like you go here and then here and back again. So the vectorial sum of these three vectors would be the zero vector. Yeah, you know, by the rules of vector addition. And this is obviously a closed chain, or in other words, a round trip. So now, but the funny thing is, or the important thing is, you can only make such a round trip if these vectors are linearly dependent, okay? Which in the end means that you could express one of them as a linear combination of the others. But since we now want to show that they are linearly independent, we have to show that such a closed vector chain is just not possible using these vectors. So in other words, this equation is only solvable using the so-called trivial solution. So this is, I can't avoid this, okay? It would be nice now to say this must be unsolvable. But actually, it's never unsolvable. It's never unsolvable because the trivial solution always works fine. It means that all these weighting factors, all these scaling factors are zero. You know what you get? You have 0 times some vector plus 0 times the other plus 0 times still another vector. But in the end, you get 0 plus 0 plus 0, because by scaling them with factor 0, you transform them all into a zero vector, and you get your zero vector here. You understand what I mean? We have to show that this equation has only the trivial solution as a single solution, and no other solution which could be visualized in a way like this. Okay, that's what we have to show. And I'm doing this in the most compact way which is possible, by using matrix notation, much the same way as we did when we solved the previous exercise sheet about systems of linear equations in matrix notation. So you see what I do? This is a vector equation, and so if I could put it in, yes, explicit form, and then you know that each or every vector equation can always be separated into its different rows. Okay, so concretely speaking, now this time we have x1 times vector a1, which is, let's look, it's 1 to 1. This is given as a row here, but actually it's meant as a column vector, which is the standard case. Okay, 1 to 1, its components in Cartesian form. I want to emphasize these are Cartesian coordinates, because we don't have any other by now. Then time x2 times, the next is 210, and then plus x3 times the third one, which is 0, 1, 2. Now, and this should be the zero vector, which is explicitly speaking the vector 0, 0, 0. Now you see what we get? If we now separate this vector equation into its three different rows, the first row is x1 times 1 plus x2 times 2 plus x3 times 0 equals 0. And you see, this is what I write in matrix notation. I read out these numbers, 1, 2, 0, 0. 1, 2, 0, then the separator for equal signs, 0. So, as always, I have removed the unknowns in our equation system, the variables, the unknowns. I have removed them and I'm just using the coefficients here. So this is the coefficient matrix of this system of linear equations, 3 equations to be solved. And this is the right side because it's a homogeneous system this time, by the way. Okay, so clear? So once you've understood this, what's happening here, I can show you the following. The only thing you have to do is take your first vector and put it as a column in your matrix. Take the second vector, use it as second column. And the third vector is the third column. And that's it. And then you're done. And here you just write zeros. That's all you have to do. And then now what's the next point? The point is we don't really have to solve this system of equations. We want to show that this is the only solution. And now it's important to understand, and this is a little bit also about matrix algebra, especially the technical term determinant. And I know that Martin started with matrix algebra just in the previous lecture, but I think he still did not talk about determinants, but I did, and I will just as a preparation now, because the determinant is what decides about the question or the answer to the question. Does a system of linear equations have a unique solution or does it not? Okay, that's an important fact. And perhaps, probably you don't know, not everybody of you knows how to calculate the determinant of a 3x3 matrix. The Saros rule is one method, or developing by one row or one row or one column. I don't want to do either. What I want to do is really use Gauss elimination, but only Gauss. Gauss-Jordan would be exaggerated now. This is because if we manage to reach the echelon form, which we will, this is sufficient to show that. So I mean echelon form really in the perfect case where the diagonal is filled with numbers, also the upper right triangle is filled, but the lower left triangle is filled with zeros. You know, this is the perfect echelon form, and it means by Gauss, this is the situation. If I use Gauss elimination, it means in the next step I could put in my results from the bottom to the top. I could recursively fill this in the other equations and then find my unique solution. And of course, the unique solution will be the trivial solution in the end. If you understand what I'm saying, you will perhaps also believe me. I hope you believe me. You just believe me that once you reach this perfect echelon form, the so-called determinant of a matrix can most easily be calculated by just multiplying the diagonal elements. And you see here, the diagonal product here is 3 times minus 3 times 1, which is minus 9. And since minus 9 is not equal to 0, it means that this system of linear equations has a unique solution. This is a general theorem which is proven. It says that only if and only if the determinant of a coefficient matrix equals 0, then it's underdetermined, and so it must have either a contradiction, which means no solution, but this is never possible with a homogeneous system, by the way, or it would even have an infinity of like I said, only if the determinant equals 0. So it's sufficient for us now to show that the determinant is unequal to 0, and that's why I use Gauss elimination, just to come yes, to reach this form. Well, let's just do it in short, because this is starting to get boring to explain every time how I eliminate. Okay, so what I do, I eliminate in the first column, as always. It means here in the second row, I did not use annotations here. In the second row, I would subtract the working row times 2. Okay, so 2 minus 2 times 1 is 0, then 1 minus 2 times 2, 1 minus 4 equals minus 3, 1 minus 2 times 0 stays 1, 0 stays 0, and then the third row, I would just subtract the working row as it is. I'm sorry, I'm just training myself to say row instead of row, because it's the correct pronunciation in the meaning of a line. As I told before. Okay, so 1 minus 1 is 0, 0 minus 2 is minus 2, and 2 minus 0 is 2. And so you see, that's the same procedure as always. Here I have to use the trick that for example, I take this row times 3, and then I add this working row times 2. That's a little more complicated. In the end, 1 times 3 is 3. Here it gets 0, and then 0 times 3 is 0, of course, plus 2 times 1, 0 plus 2 is 2, and so it goes along. But that's actually already here I would have reached the echelon form, but I made one more step and divided this row by 4, so that it's even nicer. And oh, now I see that that's actually not really it. Well, okay, you might ask, why is the determinant minus 9? Why do I use this one and not this one? Because here it would be 3 times minus 3 times 4, it would be minus 36. Well, the answer is that the determinant of this matrix is definitely unequal to 0, is sufficient to know that also the determinant of the original matrix is unequal to 0. That's part of this theorem I was talking about. The number you get is not so important. Important is just whether this number is non-zero or 0. So, okay, you see? So actually, also this original matrix has definitely a determinant unequal to 0, but it must not necessarily have this number as a determinant. So that's one way of making clear that a unique solution exists. That's all I wanted to do. But you all can believe me, if you don't understand about determinants, you will all know that when we reach this form, it's easy to calculate the solution, so that it must be unique. Just by recursively, and we can do it. You see, 1 times x3 equals 0 suddenly means that x3 must be 0. So if I fill this in here, I have minus 3 times x2 must be 0, so also x2 must be 0. And also here, I'm filling in that x3 equals 0, I get 3 times x1 equals 0, so they must all be 0. Okay, so that's all we had to show, that there is a unique solution, which is the trivial solution, and that's it. Hopefully you got it.